everyone, welcome to my booth, and I am going to talk about a very interesting project that's a collaborative teamwork between my program and Professor Phil Townsend's program at Department of Forest and Wildlife Ecology and Professor Joe Zhang's program at Department of Biological Systems Engineering at the University of Wisconsin-Madison University. And the title of the project is to use hyperspectral remote sensing and machine learning for managing potato nitrogen. It is well known that remote sensing is going to be another tool in a toolkit for monitoring the in-season plant nitrogen status and predict the final yield at the end of the growing season. Different plant nitrogen level is associated with different signals on the aerial images, which can be interpreted and translated by some machine learning models. I'm going to just briefly touch on the background knowledge about using remote sensing in plant science. So when the sun shines on the canopy of the plant, some of the light will be reflected by the canopy and then remotely sensed by a spectrometer that is mounted on a UAV or an aircraft or a satellite. The minimum unit on the ground that the light is reflected from is going to be a pixel on the aerial image. And once the light is reflected from this single ground resolution cell, it's going to be received by a scan mirror or other optics within the spectrometer. And then the light will go through a dispersing element that is usually a prism. And then the light will be split into dozens or hundreds or thousands of spectral bands. And then the energy of each of those spectral bands will be sensed by a detector within the spectrometer. The eventual quantitative measurements that we get from the spectrometer, that is either multispectral or hyperspectral, is going to be the reflectance of each of those spectral bands from the light that is reflected from the ground unit. And so that's why we can see a lot of different pixels on the remote sensing images. Because the nutrient level or disease level or abiotic stresses can all influence the health of the plant canopy, we can use the reflectance from the spectrometer to predict the plant nutrient level or other plant health status. This is a potato spectrum. I'm going to just quickly go over this picture. From left to right is the visible wavelength region, blue, green, and red. And you can see that the potato has high reflectance in the green region. That's why in our human eyes, the plants are all green in color. And then in the near infrared region, the potato has high reflectance. And again, in the short wavelength short wave infrared region 1 and 2, it has high reflectance numbers as well. So from 400 nanometers to 2400 nanometers are usually what we use as researchers for predicting the potato health or potato nitrogen status, because the plant has high reflectance in those regions. The first project I want to talk about is a UAV-based hyperspectral remote sensing project. These are some RGB images we took from a research plots with different potato cultivars and different nitrogen treatments. From tuber initiation until Wang that the potatoes are grown in central Wisconsin. And we can see that the lower nitrogen rates, under the lower nitrogen rates, the plants have light green color, and then under the higher nitrogen rates, the plants show darker green color. And we can easily eyeball those differences from the RGB images. If we translate the reflectance number into NDVI maps of the fields, we can see that the lower nitrogen rate NDVI numbers are lower, under higher nitrogen rates NDVI numbers are higher. So obviously the lower NDVI numbers means that those plants are under some nitrogen deficiency and nitrogen deficiency stress. So by the remote sensing technology, we can generate the time series NDVI maps of the field. We can monitor the plant status, nitrogen status, and then we can make decisions according to those maps. These graphs are showing how we can use modeling to predict the plant nitrogen status, including petiole nitrate, whole leaf total nitrogen, and whole vine total nitrogen. And the reflectance is from the full spectrum. Overall, we got good prediction. The R-square ranges from 0.72 to 0.82. And we're starting to build up the confidence that the remote sensing images are sufficient or good enough to predict the in-seed nitrogen status. When we're trying to predict the final yield using the in-seed reflectance, we can see that the prediction are good too. R-square is 0.7 to 0.72, but you have to pay attention to that the information that we predict the yield separately for chippers and russets. However, if we want to use the reflectance of the russets to predict the final yield of the chippers and vice versa, the R-square are pretty low. The predictions were not satisfying. So we don't know the exact reasons yet, but we suspect that there should be some genetic factors associated with the reflectance of different potato types. And in the future, if we want to do more remote sensing prediction and modeling, we should separate different potato market sectors and then work on each individually. These are from the same plots the research plots that I just showed. And these D1 to D4 maps are some predicted petiole nitrate concentration on different days of the two growing seasons, 2018 and 2019. And we can see that the prediction works pretty well. Remember, these are low nitrogen treatments, and on the prediction we see lower petiole nitrate concentration, and then these are higher nitrogen treatments. The petiole nitrate predictions are higher. So like I said, I start to build more confidence around those tools to use hyperspectral remote sensing to predict the in-seed potato nitrogen. We also found the top 20 spectral bands for efficiently predicting the potato nitrogen and yield. And you can see that overall the spectral bands are between 400 and 2400 nanometers, and most of the bands are within the 400 and 1300 nanometers, which are the visible and near infrared wavelength regions. We think that the spectral bands within those the 400 to 1300 nanometers range are the most efficient or most relevant to the prediction. The second project I want to touch on here is the satellite-based multispectral remote sensing project. This is a Google map showing different commercial potato fields in central sands of Wisconsin. And by using the multispectral images collected by this Sentinel-2 satellite, we will be able to predict the NDVI of each field over the course of the growing season. This curve is to show the average NDVI number of across the field over the season, and you can see that early in the season, because there are more smaller canopies, NDVI are smaller, and then once the canopy closed, the NDVI are higher, and we can see some NDVI difference within this field. When we try to use the multispectral reflectance to predict the final yield of those different potato fields, the prediction is pretty well. R-square is 0.82. So again, we think that this satellite image are going to be some useful information to give us NDVI maps over the course of the entire growing season, and then help us to predict the final yield based on the reflectance information that we collected during the growing season. Here are some machine learning models we're studying on, including artificial neural network, random forest, gradient boosting tree, deep learning, and so forth. You might have heard of those models. I think those models are being more and more studied on, you know, to try to explore their use in agriculture. So summary so far, we think that remote sensing and machine learning both has the potential to predict the in-season plant nitrogen status for potatoes and predict the end-of-season tuber yield. Future work needs to be specific on potato types, russets versus tubers, or other market sectors. And we should cover more temporal and spatial variability when we try to collect the ground truthing data, and then we can build more accurate and efficient models for the prediction. The long-term overarching goal is to develop some efficient machine learning models that are cloud-based and have very short turnaround time. Right now, I think one of the biggest challenge for remote sensing, the use of remote sensing in agriculture, is that the image processing time is pretty long. Growers are a little worried about the turnaround time and how efficient we can make them for guiding the in-season nitrogen management or the production management. So hopefully our projects will be helpful to address some of those problems. So finally, I want to acknowledge my funding sources from the federal level to the state level and to our university level. If you have any questions, feel free to let me know, and I look forward to the discussions. Thank you.